All right, so section 4.4 is about concavity and points of inflection. These are more things that we can consider when we're curve sketching. It's another strategy. So let's talk about what concave up and down means. So concave down looks like this. Concave down. And concave up looks like this. Exactly what you would expect. Just like parabolas opening up, parabolas opening down, same idea. Okay, but in calculus, we're going to relate it to the second derivative. So when something is concave down, we say that the second derivative is less than 0. And when it's opening up or concave up, we know the second derivative is greater than 0. Okay, and also something to remember is if the second derivative equals 0, we have no concavity. Okay, so let's take a look at an example, and we'll test for concavity. So for example, over here, we'll find the intervals of concavity for f at x is x to the 4 minus 2x cubed. Okay, so first thing we want to do is we want to find the first derivative. Okay, so f prime at x. F prime at x is 4x cubed minus 6x squared. And then we're going to find the second derivative. Okay, 12x squared minus 12x. Now we're going to use the second derivative and find out where this second derivative equals 0, just like we did with the first derivative test. So we're going to set it equal to 0, and we'll factor out 12x, and we have x minus 1. So we know that x equals 0 is a solution, x equals 1 is a solution. So now we have where our second derivative equals 0, we can run our test. So I'll make a little decision table using f at x and f prime prime at x. Okay, and we want to find out if one of the intervals is between negative infinity and 0. Then we have 1. And I need another little section over there. Terrible chart, but it's all good. Okay, so we know that if I plug in 0 into the function, I get 0. If I plug in 0 into the function of the second derivative, I get 0. And likewise with 1. If I plug in 1, I get negative 1 actually in this function. In the regular function. And f prime prime, I also get 0 because I found out that it's a 0. Now I want to test if the second derivative is positive or negative in these intervals. So between 0 and 1, I can just test a point. I can put 0.5 into this equation right here. If I put in 0.5, I'm going to get something that is negative. If I plug in negative a million or negative 10 or negative anything less than 0, I know that my answer will be positive in the second derivative. And this tells me that it is concave up in this interval. This tells me it is concave down in this interval. Okay, if I plug in 1 million into here, obviously the power is going to win, so I'm going to get a positive answer, guaranteed, and I'm going to have concave up. Okay, so now I know the intervals of concavity, and I can conclude at the bottom here. Okay, so therefore, the graph is concave up over negative infinity and 0 and 1 and infinity, and concave down over 0 and 1. Okay, so I found the intervals of concavity. Now I know the shape of the graph in these intervals, and eventually when I can combine that with all the other skills that I found this chapter, which is like asymptotes, intervals of increase and decrease, where the first derivative is 0 using the first derivative test, all these things I can put together and graph a pretty accurate sketch on a polynomial function or a rational function. So now we're going to talk about points of inflection in particular. So a point of inflection is where the concavity changes. So if I have a function that changes in concavity, you can see over here it's concave up, and over here it's concave down, here it's concave up. So where it changes its concavity is called a point of inflection. Okay, it doesn't matter how it changes. I can kind of draw any shape. It can go like this. And all these points of where it changes from concave up to concave down is a point of inflection. This is concave down, and down here is changing to concave up. So these are all points of inflection. Points of inflections are useful because we know where we have to change the direction of our curve sketching. Okay, so we're going to use that same chart we just used for the function in the previous example. So we had this function, and our chart was we had 0, we had 1. Sorry, the 1 goes here. Okay, so we determined that this is 0, this is 0, this is -1, this is 0, and then we found the concavity. This is from just the previous example. But now we're going to link it to points of inflection. So here we have concave up, here we have concave down. Therefore, 0, 0 is an inflection point. 1 and -1 is an inflection point. You might have been wondering why I included f at x in this decision table if all I need was the second derivative, right? To see when it's positive, I know it's concave up. But I want these points because these are inflection points and they're going to help me graph my function. So I can say, therefore, 0, 0 and 1, -1 are points of inflection. Okay, pretty straightforward. So second derivative test, show concavity, where it changes from concave up to concave down, those are inflection points, and that's pretty much it for concavity and points of inflection. We are going to continue to do it on a rational function, and that's pretty much it for 4.4. Pretty straightforward. It's the same thing as the first derivative test, except we're using a second derivative to test. All right, so continuing with rational functions now, everyone's favorite. Sometimes they get a little complicated. Okay, so we're going to find concavity for rational functions, and we're going to use f at x is x squared over x squared plus 1. So we want to find the intervals of concavity and the inflection points. So I'm going to write that down. Find intervals of concavity and inflection points. Yes, that's an and. Get at me. Okay, so we're going to find the first derivative and second derivative and do the same thing, make a chart, blah, 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 except finding the first and second derivative in a rational function is a little more complicated, but we know how to do it. So we're going to go f prime at x. Okay, this is quotient rule, so we're going to find the derivative of the top, which is 2x, and we're going to multiply it by the bottom, and then we're going to subtract the derivative of the bottom times the top, all over the denominator squared. Okay, now we're going to clean this up. Okay, we're going to clean it up and then derive it again. So this is going to be 2x 3 plus 2x minus 2x 3. And I can cancel out my 2x3s. Goodbye. All over x squared plus 1 squared. Okay, so f prime at x is just 2x over x squared plus 1 to the 4. I lied, to the 3. I lied again, to the 2. Okay. Now we have to find the second derivative using this function. So I'm going to go here, try to go up here because I'm going to run out of space. So I'll use a different color for the second derivative. So I want to find f prime prime at x. Why did he use light blue, you ask? Who cares? Okay, I'm going to find the second derivative, or derive this one. So I'm going to get the derivative of the top, which is 2, times the bottom, x squared plus 1 squared, minus the derivative of the bottom. Okay, so this is going to be 2 x squared plus 1 times the derivative of the inside, don't forget, so this is like times 2x. I'm running out of space here, so, and then times the top, another 2x. Okay, so a little bit complication here. Finding the derivative of the bottom, I gotta use chain rule. So I'm finding the derivative, bring the exponent down, 2 times x squared plus 1 times the derivative of the inside times the numerator. That's why there's two x's here. Okay, so I'm gonna put this all over x squared plus 1 squared. And now I'll start cleaning it up. So this is 2x squared plus 1 squared minus 2, 2, and 2 is 8x squared, 8x squared, x squared plus 1, all over x squared plus 1 to the 4. What am I doing? To the 4. Okay, and I notice that there's an x squared plus 1 in every single term, or I can factor out an x squared plus 1 on the numerator. I'll choose that option just so we can see the cancellation, because we tend to struggle on those cancellation steps. I'm going to take out a 2 as well. 2x squared plus 1. And I'm left with an x squared plus 1 over here. A 4x squared in the front over here. And that's it. And this is all over x squared plus 1 to the 4. So in factored form here, I can see that I can cancel this guy out and one of these. So I'm left with 2. I can clean this up actually. This is negative 3x squared plus 1 over x squared plus 1 to the 3. Okay, if you want to rearrange that or factor that in, you can. I don't really care. Okay, so now we want to find zeros. This is the second derivative. Right, we want to find out when the second derivative is 0. So we just look at the numerator. When will the numerator be 0? No problem. So we set negative 3x squared plus 1 equal to 0. All right, so I just found out that the longest video I can take on my phone is 5 minutes long. So we were probably almost there. We stopped at the numerator, finding out when it's 0. I found out when the numerator is 0 here. Set it equal to 0, solve, I get plus or minus 1 over 3 under the square root is x. So I make my decision table using these two values, plus and minus 1 over root 3. Okay, root 1 is just 1, so I just simplified it. Not really, because there's a root in the denominator, but who cares? So I create my decision table using f at x and f prime at x. I plug in these two values of when this is 0 into my function, and I'm doing this to set up my inflection points. So I figure it out, I plug it in, get 1 over 4, plug this in, get 1 over 4 into this function, by the way, which is almost disappeared. This x squared plus 1 at the bottom. Okay, that's how I get these values. Then I plug them into my derivative. I know they're going to be 0 because I found out that they're 0. So these are guaranteed 0. And I'm going to test points in this interval, negative 1,000,000, plug it in, negative 100, whatever you want, into here, and I get negative. This means that it's concave down. Okay, I'm going to plug something into the function, the second derivative in this interval. 0 is probably my best bet. I'm going to plug it into this function, and I'm going to get a positive answer. Okay, remember, use your answer key on your calculator to do this quickly if you want. And then I'm going to use this interval, plug in 10, 5, 1,000,000, whatever you want in your calculator, and I'm going to get a negative answer here. So now I know the concavity based on the second derivative being positive or negative. So I'm done, pretty much. I can conclude. Find the intervals of concavity and inflection points. So the graph is concave up, where it's concave up, right here, between these numbers. Interval notation or set notation, whatever you want. The graph is concave down in this interval, right? Negative infinity to this point, and this point to positive infinity. So that's what this says in interval notation. Okay, in the last part of the question, I have to find my inflection points. So the inflection points are where the concavity changes from concave up to down or vice versa. So this is concave down, this is concave up. This is my inflection point. This is my other inflection point. There they are. These are my inflection points. And that's it. I've answered the question using a rational function. Okay, so here we're going to use the second derivative test. To find local extrema. Okay, so I'm just going to write a statement here. So if the second, terrible, too many F's. If the second derivative at point x or we can call it point C, critical point, is 0, we may have a local min, max, or neither. So we may have a local min, max, or neither. Okay, I know we talked about this in class, but just to say it again, how do we have neither? So we know we can have a min or a max if f prime at C is 0 and f prime prime at C equals 0. This is a minimum. Okay, they're both 0. But we could also have something that looks like this. And this point also would have f prime at C equals 0, f prime prime at C equals 0. And this is no local extrema. Okay, or we can call this also an inconclusive case. Inconclusive. So our second derivative could have an inconclusive case, which means there's no local extrema. So let's show you how that looks like in an example. Let's say we wanted to find, okay, we want to use the second derivative to find the local extrema. Find local extrema for the function f at x equals x minus 1 to the 3. Okay, so we're going to find the first and second derivative. First derivative, 3x minus 1 squared. So x is 1 for our first derivative. And we're going to plug it in to find that f at 1 equals 0. We always want to find out what the value of the function is, because whether it's a minimum or a maximum, this tells us what the value is. Okay, now I'm going to find my second derivative. Okay, and if I plug in f prime prime at 1, I'm going to get 0. Okay, and this is an inconclusive case. Why is it an inconclusive case? Make a chart. I'm going to use my first derivative test. Okay, so in my first derivative test, I have one value. And if I plug it in, I get 0. Okay, if I plug it into this function, the initial function, or the second derivative, first derivative, I'm going to get 0. If I plug in a number less than this, I'm going to get something positive. If I plug in a number greater than this, I'm going to get something positive, because this is a square. It doesn't matter what I plug in, negative, positive, this is going to be positive, which means this is increasing in this interval, this is increasing in this interval. When I go from increasing to increasing, this is what an inconclusive case is. It looks like this, the function. So while this is the slope of my tangent being 0, I don't have any change in concavity. No, wait, I do. I do have a change in concavity. This is still an inflection point, but I don't have any local extrema. That's what I meant. Okay, there's no max or min. So while this is 0, you'd think there's a maximum or minimum. There is an inconclusive case where it's not the case. So I want to test it using my first derivative test, find out that it's increasing and increasing, therefore no local extrema is my answer. Okay, and this is an inconclusive case.